10 million people open the same app at the same second. Every one of them fires a request at the same address. And nothing breaks. No spinning, no errors, no waiting. Stop and sit with how strange that is. No single server on earth can answer 10 million requests at once. So how does that one address never fall over? Something is sitting in front of it, making a decision. For every request, millions of times a second, that you never see. Most engineers can name that something. Almost none can explain how it actually works. Today, you will. This is the load balancer, the one piece almost every system design interview eventually circles back to. Every single server has a ceiling. It does not matter how much you optimize the code. At some point, the requests arrive faster than one machine can answer them. When that happens, latency climbs, the queue backs up, and eventually requests start timing out. You have two ways out of this. You can buy a bigger machine, or you can buy more machines. The first path runs out fast. Hardware has limits, and it gets expensive in a hurry. The second path is the one that scales. But the moment you have more than one server, you have a new problem. Who decides which server each request goes to? From the outside, it looks like everyone is talking to a single server. One address, one machine, somehow answering the whole world. That illusion is the entire point. Because behind that one address, there is no single server at all. There is a whole pool of them. And the load balancer is the only thing the outside world ever actually touches. Every request hits the load balancer first, and it quietly forwards each one to one of the servers hidden behind it. Behind that address could be 3 machines or 300. The client never knows and never needs to. This is what makes it powerful. You can add servers during a traffic spike and remove them when it is quiet. You can take a server down for an upgrade in the middle of the afternoon. It simply leaves the pool, updates, and rejoins, while the front door never blinks. The pool changes all day long. The address never does. Here's the distinction that separates a real answer from a vague one. Load balancers work at one of 2 levels, and interviewers love the difference. The first is called Layer 4. A Layer 4 load balancer looks only at the network information, the source address, the destination address, and the port. It does not open the request. It does not know if you asked for a video or a login page. It just sees a stream of bytes headed somewhere, and it forwards that stream to a server. Because it never looks inside, it is extremely fast, and it works for any kind of traffic. The second is called Layer 7. A Layer 7 load balancer actually reads the request. It can see the web address you asked for, the headers, the cookies, all of it. That means it can make smart decisions. Send every request that starts with /video to the video servers. Send everything that starts with /API to the API servers. The trade-off is simple. Layer 4 is faster and dumber. Layer 7 is slower and smarter. And in practice, you often see both at once. A Layer 4 balancer handles raw speed at the very front. This is what a cloud network load balancer does. Then a Layer 7 proxy like Nginx, Edge, A-Proxy, or Envoy sits closer to your services and routes by content, fast and simple on the outside, smart and content-aware on the inside. Once you have a pool of servers, the load balancer needs a rule for picking one. The simplest rule is round robin. First request goes to server 1, next to server 2, next to server 3, then back to server 1. It is fair and it is easy. But it assumes every server is equally free, which is often false. A better rule is least connections. The load balancer tracks how many active connections each server is handling and sends the next request to whichever one is the least busy. This handles the real world, where some requests are quick and some hang around for a while. There is also weighted round robin, where a more powerful server is told to take a larger share. The rule you pick is not academic. With plain round robin, a slow request can land on a server that is already buried under other slow requests. The balancer does not know and does not care. It just keeps handing out turns in order, and your unluckiest user pays for it. Least connections avoids that trap. because it actually looks at how busy each server is before it decides. Now for the technique that shows up in every serious interview. Sometimes you do not want requests spread evenly. You want the same key to always land on the same server. Think of a cache. If user 1000 always hits the same cache server, that server stays warm and fast. The obvious way to do this is to take the user's identifier and take it modulo the number of servers. User number modulo 4 servers gives you a server. Clean and simple until a server dies. The moment you drop from 4 servers to 3, that modulo changes for almost every key. Nearly every user suddenly maps to a different server, every cache is cold, and your database gets hammered all at once. Consistent hashing fixes this. Instead of a flat modulo, you place both the servers and the keys around a ring. Each key walks clockwise around the ring until it meets the first server. Now, when one server disappears, only the keys that belong to that one server move. Everyone else stays exactly where they were. There is one catch. With just a handful of servers on the ring, the load can land unevenly. One server owns a huge slice, another owns a sliver. The fix is virtual nodes. Each real server is placed on the ring many times over, under many different points, so the keys spread out smoothly no matter how few machines you actually have. This is the detail interviewers love to hear, and the one most people forget. Either way, you go from remapping almost everything to remapping almost nothing. A load balancer is only as good as its knowledge of which servers are alive. If a server crashes and the load balancer keeps sending it traffic, every one of those requests fails. So the load balancer constantly checks the health of its pool. There are 2 ways to do this. Active health checks mean the load balancer reaches out on a schedule, asking each server a simple question. Are you okay? A healthy server answers quickly. A server that misses too many answers in a row, say 3 checks, a couple of seconds apart, gets pulled out of rotation. Passive health checks work the other way. The load balancer watches the real traffic it is already sending, and if a server starts returning errors or timing out, it gets marked unhealthy. The best systems use both. And here is the part that makes it matter. Picture a server crashing at the worst possible moment, right in the middle of peak traffic. Without health checks, every user routed to it hits an error. With them, the load balancer has already noticed the missed replies and pulled that server out, so the very next request quietly lands on a healthy machine instead. The server failed. Nobody outside ever knew. And when that server recovers and answers cleanly again, it just as quietly slides back into the pool. Sometimes a user has to return to the exact same server every time, and that quietly breaks load balancing. Picture a server that keeps your login session in its own memory. If your next request lands on a different server, it has never heard of you and logs you out. Sticky sessions patch this by pinning you to one server for the whole session, usually with a cookie the balancer hands out. It works, but it fights everything a load balancer is for. A pinned user cannot be moved, so traffic stops spreading evenly. And when that one server dies, everyone pinned to it loses their session at once. The cleaner answer is to not need stickiness at all. Move the session into a shared store, an external cache every server can read, and now any server can serve anyone. The balancer goes back to its real job, and no single machine holds something the others cannot. So here is the whole picture. A load balancer is just a front door that lets you scale out instead of up. Everything else today was really one decision, made well, which server right now. Layer 4 versus Layer 7 decides how much it reads. The algorithm decides how it spreads the load. Consistent hashing keeps the same key on the same server. Health checks keep the dead ones out. And shared session state lets any server answer anyone. But if you take only one idea from this video, take this one. Scaling was never really about adding servers. It is about deciding where each request should go. Every algorithm, every ring, every health check is just an answer to a single question. Where does this request belong? Answer that well, and whether you run one server or 10,000, it stops being the thing that breaks. So the next time someone asks what happens when one server isn't enough, you won't reach for a word. You'll reach for the whole idea. If this made it click, subscribe. The next one drops Thursday.